right, here is our brand new chapter of waves. More importantly, dealing with waves is we are going to be looking at simple harmonic motion. So all of us know these waves as they move up and down through our page. But what simple harmonic motion is talking about a pattern that is repeating itself. So these waves, based upon their frequency and their wavelength, follow a particular pattern as they move through space and time. So as we look through these patterns, we're going to start to develop different ideas of how these waves look and behave. All right, first we're going to look at a particular problem where we have a mass M that's attached to a spring, and typically they're horizontal and it's moving back and forth in simple harmonic motion. And we want to be able to solve for the maximum velocity that this object is going to have. Well, we know that its potential energy and its kinetic energy at all times, when you add those together, have to equal its total mechanical energy. So if I have max potential, I have no kinetic, and if I have max kinetic, I have no potential left. There's the bell. So what we're looking for is a way to solve for my maximum kinetic energy. So I know when I have maximum kinetic energy, I don't have any potential left. But I had to start with a particular potential amount. So where x is the maximum amplitude, we are going to insert a. So a was the farthest apart. So let's say I pull this back all the way over here to position a away from my equilibrium position. So this would be positive a, and that would be negative a in terms of amplitude. So in order to solve for Vmax, you rearrange the 1/2s go away, looking to solve for m, so it's k over m, and then all under the radical, a becomes x, and it pops out. So this is the equation that you have in your notes in order to solve. Let's see what solving looks like. All right, what's the maximum velocity for a spring with a mass of 2 kilograms at the end, with a k value of 200 newtons per meter, which reaches a maximum amplitude of 0.5 from equilibrium? So here's my spring, 2 kilogram mass, 0.5 plus, negative 0.5, and this is its equilibrium position. So I write my equation, V max is equal to A K over M. K is 200 divided by my mass of 2 kilograms, all under the radical. 200 divided by 2 is 100. 100 under the radical is just 10 times 0.5 equals 5 meters per second. When would it reach its maximum velocity? Well, it'll reach that right as it's going through its equilibrium position. So it's either going to be at maximum velocity when it goes through its equilibrium, and its velocity all the way out here is going to be 0. But I am reaching my maximum amplitude. So I have maximum potential here at this point and maximum kinetic here as I go through the middle. So we know about the period. The period is the total time it takes to do one full oscillation. And the frequency is the number of oscillations completed in 1 second. They are inversely proportional to each other. So for things that take a real long time to go around in a circle, we use the period. For things that move really, really fast, we use the frequency. And you can use them interchangeably by just taking the inverse of whatever you're looking for to solve. So let's look at an example of that as well. All right, so now we're going to find the k value of a spring with a 1 kilogram mass attached to the spring, pulled 2 meters from its equilibrium position, and undergoes simple harmonic motion with a frequency of 8 hertz. So a frequency of 8 hertz means it takes 1/8 of a second to do one full back and forth. So here's my spring, 1 kilogram mass attached to it. It goes 2 meters from its equilibrium position, and the frequency is equal to 8 hertz. So my equation for period, T is equal to 2 pi m over k. If I'm looking to solve for the inverse of that, so frequency is equal to 1 over the period. So either I can solve for the period using these values and then take the inverse of that, or I know that the frequency is 1 over 2 pi, and then I just flip what I have inside of the radical. So both of these work. It just depends on what you're looking to solve for. All right, so since I'm looking to solve for k, I'm going to take this guy and plug him in over here. So now I have 2 pi f, and now I have to square both sides. Now I just have k over m, so times m is equal to k. And 2 pi f squared, 2 pi is 6.28 times 8 squared gives me 2,514 times 1 is equal to k. So k equals 2,514 newtons per meter. So it's just knowing how to move back and forth between the equations and how to solve for period and frequency.